Right, thank you. That was a long introduction. I think the point of it was just to say that I'm not a Hitachi employee in any way, shape, or form. I'm actually a microscope user and a microscopist primarily, and we happen to have a very good collaboration with Hitachi, in particular on that one instrument that I'm going to be showcasing. And so this talk was meant to be a little bit of a longer presentation with a few more applications than what I'll be hopefully presenting slightly later in the week on Wednesday, which is slightly shorter, so 12 minutes. I was very happy to be able to add a few more slides. I'm notorious for packing something like 50 slides into a 10-minute talk and then having to rush through them. So this time I have the pleasure of being able to go a little bit more slowly than usual. I'm in front of you this evening, but really that's very much a group effort. My name's Quentin, but the people who did a lot of the work, certainly at SuperSTEM, were Demi Kepapsoglu, partner in crime, who's been working at SuperSTEM with me for the last 15 years, and Sean Collins, also from the University of Leeds. And most importantly, we basically just came with maybe questions, sometimes questions that people thought were a little bit too difficult to answer, and then turned out they were answerable. But the people who were the most important in the whole story of this application are the people at Hitachi. So in particular, Tsunayoshi-san, Kaji-san, Yamazawa-san, Okada-san, Saito-san, who designed the various parts of the instrument, and then Mike Dixon, who's the Hitachi representative in the UK, and whose lab happens to be about 200 meters, 300 meters away from our own laboratory, and that's where that whole collaboration came about. So just to give you a very brief intro to again explain where this whole thing came from and why I'm here this evening talking to a Hitachi audience about a Hitachi microscope when I'm really just a scientist at a national laboratory. SuperSTEM is located between Liverpool here and Manchester. That's the little red dot there. On the one day in the northwest of England when it doesn't rain, we're sometimes able to fly a drone and take a nice picture of the lab. SuperSTEM is that tiny little lab over here. And again, you see the most important room in the building, which is the coffee room where all our stupid questions are asked and sometimes answered. But that's certainly where we spend the most of our time. We're a user facility, so that's the reason, again, why this machine came about. We like to describe it as having a bunch of toys that we like to share with our friends so that they can come and play with us. And by play with us, I mean people essentially have scientific questions, and we happen potentially to have instruments that can answer parts of those scientific questions. That's made available through a wide range of scientific collaborations, but also through various universities in the UK. So I'm affiliated with the University of Leeds, as Inoue-san said. Demi Kepapsoglu, whose name I mentioned earlier, is affiliated with the University of York. Sean Collins is with the University of Leeds. And we have a very large network of academic institutions that we work with. SuperSTEM, as the name indicates, it sounds like a little silly name for an electron microscopy lab. It was coined by Professor Mick Brown at the sort of 1997, trying to pool together resources in the UK, certainly just when aberration correction was starting up. So 1997 is the first time when aberration correction in STEM was demonstrated by Andrzej Krywenek, whose booth is just right next door. And SuperSTEM was created as the vehicle for offering access to new technologies, new instrumentations, certainly to the UK community, but also worldwide. So it's a silly name, but it's stuck because people remember it. And really what we do is scanning, transmission, electron microscopy, and certainly for the last 10 years or so, we've been focusing on EELS, electron energy loss spectroscopy specifically. So high resolution, both spatially, but also in energy in various ways. So we have various instruments. The last two that we've installed are these two. So they're all neon instruments, and they're really low kV in the large ecosystem in that they only reach 100 kilovolts and below. So 100, 80, 60, 30 kilovolts is roughly what we do, with aberration correction and monochromation to allow us to get to about 10 milli-electron volts or below, but certainly trying to look at electron energy or spectroscopy. When the lab was created, and again, I'm sorry if I'm giving you a long-winded walkthrough where we came through this collaboration with Hitachi. So back in the late 90s, people said, we're going to focus on microscopy, EELS, imaging, aberration correction. This is what we know, this is what we do. And we're going to let people deal with sample preparation and sort of the upstream work, a lot of the upstream work that is needed before you can actually add the icing on the cake, the cherry on top with the really high resolution stuff. So we didn't really worry too much about sample preparation or screening of samples or nanometer or tens of nanometers or hundreds of nanometer screening, although screening sounds bad. It really means all of the information you need before you start looking at the one single atom that's sort of sitting somewhere that you're going to go and poke. That's changed a lot because the more you use low kilovolts microscopes, the better your samples need to be. And maybe if I go back one slide, in sort of serendipitous, I don't know if it was by accident or by design, but Hitachi High-Tech Europe actually placed their demonstration lab in this building over here. And if you'll remember, our building, SuperSTEM, is somewhere there. So it's literally 200 meters away from the main demonstration lab in the UK for UK, Scandinavia, and other northern countries. And basically, we can just walk across the roads and talk to Hitachi colleagues and sort of play with instruments at the time. So that's not to say that that was the defining factor, but it certainly was in factor in our thinking that we needed a way to look at sample in slightly better ways. And we've actually acquired a few years ago one of Hitachi's other instruments, a FIB, that I'm not going to talk about at all. But the point of that instrument was it happens to have a side entry stage, so you can put a normal TEM rod, and that side entry stage happens to be perfectly compatible with the SU9000, which is the object of this particular talk. So the whole idea was to be able to go from making a sample, and again, I always horrify every single colleague of mine when I tell them, if you want to do atomic resolution EELS, your sample will need to be about 10 to 20 nanometers thick. And usually they say you're asking for the moon. Yes, we are asking for the moon. But if you happen to have your FIB right next to a low KV stem that can actually look at the exact sample, so milled on the side entry holder, take the side entry holder out of the FIB, put it in the SEM, look at it, then that's exactly what we want. And so as part of the package with our NX5000, our FIB, we were introduced to this instrument, which is what I'm going to be talking about a little bit later on, and that's the SU9000. I should really preface this that we didn't invent any of this. We're not claiming to be the first one to have this instrument by any stretch of the imagination. It's been in the wild for quite a few years. It just so happens that our particular focus on low KV EELS, and particularly atomic resolution, was one that was not necessarily shared with many of the other owners of microscopes from the SU series. And so when we were told that this was an instrument, and again, I'll defer all technical questions to my Hitachi colleagues, I'm really not trying to sell it or to pretend that I know everything about the actual instrument itself. I'm just here to sort of give you a little bit of a story about how it came about and how we thought it could be used in a slightly different way from a normal SEM. So when we were told that we could have, in addition to our FIB, an instrument that could go from, say, 500 volts all the way to 30 kilovolts, do about 2.5 angstrom resolution in bright field STEM, so in transmission geometry. Also have a high angle annular dark field detector in essentially a low KV STEM. And a lot of people would call it a toy STEM. It really isn't a toy STEM. It's just a simple STEM that you can use in the same way that you would use an SEM. But then the clincher came when people told us that all the way back in 2016 already, you could actually use an EELS system and adapt an EELS system to this instrument. And that was really something that caught our attention, and thought if you have a cold field emission source, so 350 millielectron volt energy resolution, 2 angstrom, 2 to 3 angstrom spatial resolution, provided your sample is good enough. But remember, our focus was to make samples thin enough and good enough to get there. Then you could do exactly what we do with what I call our big machines, but on a slightly smaller machine that looks something like this. And I really need to give a shout out to all the people who've done work on these machines before. So the first paper was by Kono-san all the way back, but there's also a really lovely paper by Nicolas Broduche from Renald Gauvin's group at McGill, who have a machine like this, and they've explored a lot of the applications and a lot of the techniques you can put on one of these machines. We're really just coming on top of this and looking at a small angle, and that small angle is, can we do things that you would normally not think of doing in an SEM? And I should have said, if anybody has any question, please interrupt me at any point, otherwise I'll be talking at you for the next 2 hours. As I said, I can bore you to death until you've got tomatoes to throw at me. That's no problem. I'll be more than happy to keep you away from drinks.
And that is image from SEM?
Yes. So again, these are not our images. I'll show you some even better. Well, not even better. That's really mean. Some slightly higher resolution images. So not better. So this is a bright field STEM image, so using in transmission. I believe it's a silicon sample, and I know it does sound rather weird to see something like 2.1 angstrom resolution at 30 kilovolts. If you just do the calculation, the probe size shouldn't really get you there without monochromation. So it's 300 millivolts energy resolution. So your CC delta E, your chromatic contribution is small, but not that small. The way they got to fringes in silicon to 2.1 resolution was by playing with the contrast Fourier transform, essentially. So if you change a little bit your focus and if you play with the thickness, you can get those fringes in HRTEM to actually show up at resolutions or information transfers that are somewhat higher than you'd expect. So that's the trick there. I'll show you images that are not bright field, but had FSTEM, and for those, the only trick is a little bit of help from channeling through the crystal, but otherwise none of that CTF playing around. So, and that's a multi-wall carbon nanotube, and again in the same instrument, showing the 2.3 angstrom and 3.5 angstrom spacing of carbon. So these are from this machine, 30 kV, and again, I should really insist that I'm not trying to sell it in any way. We bought one, but the beauty of this is for us. So we used to using aberration corrected instruments with 200, 300 power supplies. Every single lens is controlled individually. You have to correct the instrument, make sure everything works. This has 3 knobs, is what I tell the students when they come and see us. Magnification, focus, and if you really need to, astigmatism. But other than this, it's an SEM. And then within 5 minutes of inserting the sample, you get images that are of the order of 2 angstrom resolution. And if you happen to have EELS, you also get sort of 0.3 EV resolution, so you can tell the difference between graphite, diamonds, graphene, 1-layer graphene, 5-layer graphene, 10-layer graphene, which is, again, none of our work. That was done by Tsunoshi-san, actually it was an M&M proceeding, 2016. Again, we're not pretending this is all new, it's just that people haven't really used it as much as they should have, because this is just amazing capability in an SEM at 30 kV. So, with all this said, the question we came with our big boots when our friend Mike Dixon said, well, we can have this SU9000 was, well, that's all nice and well, but what we do is single atoms. Can we do single atoms or atomic resolution in the SEM? That was really the starting point of the project. This is just a little cartoon, and I'll show you where we get to that. This is not the sort of images we get in this machine. This is the same sample, but this is a bulk sample. It's not regular anything. This is the point at which maybe if anybody has questions, I'll have to defer to Muto-san if he has any answers for this. I stole this shamelessly from sales material that I was given quite a few years ago on the SU9000. It's a very, very basic schematic. I'm going to be even a bit provocative in saying it's completely wrong. It doesn't even have an objective lens, so I don't know how the secondaries go back up in this particular case. It's just to show you where things are and what this machine is. As far as we're concerned, it's exactly the same as our machines. It's very simple. It just has a source, some sort of lens focusing the probe on the sample, and then a bunch of detectors. What's really important is it has this EELS spectrometer at the back end, which allows us to do EELS, but also EDS, so we can do EELS, EDS simultaneously. And we're very strongly pushing our friends and colleagues in R&D to also add things like 4D STEM, maybe some sort of post-specimen optics, without making it too complicated, but certainly making it even more flexible. It has 2 detectors in EELS, and again, Muto-san can answer if you have any questions. As you would in any EELS spectrometer, you will have a CCD camera, so you just spread your beam into your rainbow illumination, and then you put this in, on your CCD, and you get your zero loss, your plasmon, and your new core loss. But it also has this, what they call elemental mapping detector. Essentially, that was designed, as far as I know, and again, I'll defer to my colleagues, for the semiconductor industry, as a way to do very quick elemental mapping for low Z elements. So carbon, silicon, et cetera, nitrogen, when the new ray or the new era EDS detectors were not available, and so this is not a CCD. These are basically just photomultiplier, so scintillator photomultiplier 3-stripe, which allows you to do 3-window or jump ratio mapping very quickly. So you can either use this method as a 3-window mapping that doesn't give you a spectrum, that just gives you a map, or just deflect the electrons onto the real camera and then do what you would do with what we normally do, which is point-by-point STEM EELS. Right. So far, so good? No question? No? Right. So what can we do with this? We went to Japan to try out the EELS, and we came with about 15 different sample types, thinking maybe one will work, to the great horror of our colleagues, Anashi-san and Kaji-san, who thought, oh dear. But then every single one worked, so I'm going to be able to show you at least 4 or 5 of them and explain where they came from. So our first idea was something that came from one of our collaborators and something we do on our what I call our big machines. So these are carbon nanopepods. That's a group of André Chlobistov at the University of Nottingham, and he's got a whole load of chemist wizards who are able to take a buckyball, so C60 carbon ball, open it up chemically, stuff the molecule, one molecule inside the buckyball, close the buckyball so that it's all encased, and then each of those buckyballs, they then put them into a single wall carbon nanotube. So you have like a nano test tube, which consists of a single wall carbon nanotube, inside which there's a string of buckyballs, and inside each buckyball, there's some sort of molecule. So that can be, we've looked at HF, water, deuterated water, D2O, H2O, all sorts of molecules. Our most recent obsession has been with noble gases, individual noble gas atoms of noble gases, because those are extremely difficult to isolate otherwise. Krypton, argon, neon, you name it. And at the time we started this project on the SU, we were trying to look at single neon or krypton atoms within a carbon nanotubes. These are images from our big machine. Again, this is just to give you a little bit of background and why we thought that would be interesting to look at. It's interesting because it's a very heavy atom, krypton. It's got a high Z, so it gives you really high Z contrast inside a carbon matrix, and it's very thin. You just have the carbon nanotube and a C60 buckyball. And we know we can map it in EELS because we've done it, both in argon and krypton. And again, I can bore you to death to explain you that if you illuminate these things a little bit too much, the C60 buckyballs sort of merge together, and you end up with essentially a tube with a string of single krypton atoms, and essentially it's a 1D gas. So you have krypton atoms that are sort of confined within a 1D container, and this is what you see in images and also in EELS. But we thought that might be a very good system to go and look at in the SU9000. So I'll cut to the chase and show you what essentially we managed to obtain with it within about, I don't know, 10, 15 minutes of showing up on the factory floor. So these are your carbon nanotubes. I'm going to look at this way because otherwise the contrast is a little bit poor. And actually the contrast is poor. But perhaps I'll go quickly and then you can go and look at my screen later on. The bright field stem is slightly more obvious than the dark field stem in these images, but these are individual carbon nanotubes, and you can just about see the string of pearls within, which are those buckyballs. And unfortunately, as I said, the TV doesn't really show up nicely, but maybe if you sort of squint along here, you can definitely see a string of slightly brighter contrast. And that contrast wouldn't be there if the single krypton atoms were not imaged. So if you do image simulations using the exact same parameters as what we have for the SU, we wouldn't be seeing this contrast unless we were actually imaging individual krypton atoms. Again, they're more obvious on the image on my screen. You're very welcome to come and take a look at it slightly later on. But we were really pleased to see this literally within a few minutes. So that sort of got us thinking that we might actually be able to do the same trick as on our big machine and actually map these. And I'm going to go quickly over this because that's sort of the intro on what we can do. The short answer is we probably see strings of krypton atoms. So this is an EELS map looking at the krypton edge in the SEM at 30 kilovolts in a bundle of carbon nanotube. The only issue we had is the instrument was on a factory floor, so you had people essentially cranking up cranes to put big lenses onto a microscope right next door. People were just walking around all the time. So stability wasn't great, and we were not able to actually look at a single individual nanotube for long enough to do an EELS map. But we think that this bright line over here is actually the map of that krypton edge within the carbon nanotube bundle, and it really is just a string of single atoms. So if we couldn't do very stable acquisitions with just one carbon nanotube, the next best thing was to go and look at bulk samples. And again, this is where we come from. We want to look at bulk samples in transmission, so not super thin, but samples that have been thinned thanks to either fib or crushing. And again, these maps and these images are not from the SU9000, but from our big machine looking at 100 kilovolts this time on various edges, so barium, neodymium, titanium, and oxygen of what I think a rather beautiful structure. It's an electroceramic that is used for all sorts of applications from the group of Robert Free at the University of Manchester. And this sample was originally sent thinking it would be nice to look at in EELS because the distance between the various areas where we've got just neodymium, which is what I'm sort of pointing out over here, or barium, is large enough. Remember, it's not a corrected machine. It has 2.5 angstrom image resolution or probe size. So we can't go and look at individual columns. What we can go and look at is planes that are separated well enough. So what does it look like in practice? This is the very same sample. So we took the same sample that we looked at 100 kV to the factory marine sites in Japan and looked around for the exact same grain, tilted it on axis, and then what you'll notice is that we've got certainly plane resolution. We'll see higher resolution in a minute in bright field stem, dark field stem, HADF stem, but also in a secondary. So within the exact same system, you get all three images giving you lattice resolution without much of a problem. And again, that was about 5 minutes after locating that grain, tilting it onto zone axis. And then we thought, great, we've got it, let's do some EELS. And I'll point to two things to this, and then I'll promise I'll get to actual atomic resolution EELS in a second. Number one is we are doing EELS at 30 kV on a 30 nanometer sample. So it's not been optimized in any particular way. But we're still managing to resolve edges, the barium edge, the neodymium edge, at 800 or even near 1 kV energy loss. Not great, it's a little noisy, but it's there. So it's very possible, you don't have to really push it, and that works rather beautifully. What's interesting also is if you go across in 2D one of these very thin areas of the samples where you've got those bright lines, which of course correspond to the areas where you've got more neodymium. And again, I'll have to apologize for the rather poor contrast, but you get barium bright in red here, neodymium bright in yellow, barium bright in red, neodymium bright in yellow, and then at the top here, it becomes a little bit mushy because that was amorphized all over here. So that looked great. Can we push it even more? And the way we pushed it is by selecting a specific sample system, yet another one from Robert Freer at the University of Manchester. And that is, again, a perovskite complex oxides. Again, a sample that is normally reserved for 100 kV or so. And you'll notice that this perovskite structure, if you're familiar with that particular class of materials, normally it's a very simple cubic system with really heavy ions on the corner of a face-sharing cube, except every other A site, which is this bright dark line over here, has no intensity at all. So all of the heavy atoms in there, which would normally be lanthanum, are missing. What does that mean? That means that if you do a map of this, lanthanum appears every 8 angstroms also. So that's spaced enough that you should be able to detect those things perfectly as you go from one plane to the other with a sort of spatial resolution that we have. So now to the clincher. How does it get there? Well, again, exact same sample, exact same area on the sample as what I showed you just a slide ago. Previous slide, 100 kV. This is 30 kilovolts. Information transfer all the way out to about 2.6 angstroms, both in bright field and dark field stem. So again, no trick there with phase contrast transfer function. It really is just probe propagation, giving you 2.5 angstrom or so spacing in your image. Just as a little bit of trick, something that I tell my students never, ever, ever to do, Fourier filtering. If you actually Fourier filter things, you get an image like this, and if you superimpose this little image here, which is the 100 kV sub-angstrom resolution image of the structure on top of this green-blue image, which is at 30 kV, then there's a very good correspondence. So that just told us we see really the structure exactly as it needs to be. Now to the yields. Again, instead of doing 2D maps this time, we went for line scans to start with. And again, you'll notice that those bright lines correspond to the areas where there's lanthanum. The dark lines correspond to the areas where there's no lanthanum. Lanthanum is heavy, therefore it appears bright. Where there's no lanthanum, that gives you a dark line. And if you do an EELS line scan across, you have the image contrast at the top right over here, which shows you ups and downs, troughs and valleys corresponding to bright line, dark line, etc. And in perfect registry, you get an intensity increase in the lanthanum edge, which is again at 832 eV at 30 kV, so no problem mapping that. And actually getting what we would call towards atomic resolution. I'm never going to be able to get the same sort of resolution as I get with a probe-corrected machine. But given that this took quite a bit of effort to set up, understand how to get this image, this data, but otherwise could be possible to do within about 20 minutes of inserting the sample. That provides really capabilities that we were not expecting. One line scan is good. A 2D map is better. I don't know if you remember, but I told you there were 2 detectors in this machine, either just a camera or a 3D stripe, where you could do 2D 3-window or jump ratio. So we did exactly the same thing on the same structure, but this time doing really fast scanning instead of having to try and beat drift. And again, I'll apologize for the contrast, but the 3-window method really shows, hopefully you can see the ups and downs and the troughs bright lines, dark line, bright lines, dark lines corresponding to the atomic resolution mapping. So I'm looking at the clock and I'm realizing that I've got 2 more very short stories to tell, so I don't want to keep your time too much, but if there are any questions, please don't hesitate to ask, and otherwise I'm here all week, so please do come and find me. The one thing that we also wanted to add to this whole story is we did all of this at 30 kilovolts, but we have an SEM with an EELS spectrometer, so why go fast with our electrons? Why not try and use very slow electrons that are good little tortoise and do EELS at very low kV primary beam energy? Can it be done? And again, that's a question we asked to the designers at the factory, who, when we first asked the question, looked at me like I was some sort of madman, saying, "You complete idiot, that's never going to work." Lo and behold, give it a little bit of elbow grease. This is boron nitride. Again, one of the samples we brought thinking it's never going to work, but worked within about 10 minutes. Going from 3 kV to 30 kV, looking at the boron and the nitrogen K edge. This entire series was literally 3 hours work, switching kV, waiting 2 minutes, getting the EELS, and then being able to pull the boron and the nitrogen K all the way down to 5 kilo electron volts. So why would you be interested in doing this? Well, many reasons. If you're looking at your sample at 5 kV and you want to do some sort of EELS with it, you don't have to switch, you don't have to go to another machine, it's right there, it's possible, it's alignable. You can do EELS mapping, you have the same resolution, potentially even slightly better resolution because your CC delta E might actually be better at lower kV than at higher kV. You have higher cross sections in EELS at lower kV, so you get slightly more, a slight boost in signal. When I first showed this, there was only one person in the room who looked at it and said, "This is weird because your boron K, pi star, and sigma star ratio changes with kV." This is not physics, this is just, well, it is physics, but this is not due to the change in kV, it's just due to the change in collection angle as the kV changes, because the collection efficiency changes. You don't have, in this particular machine, a post-specimen lens to recombine the electrons into the spectrometer. But there might still be some really exciting science to do there. Some people who've read the EELS literature from way back when will remember resonant EELS. So if you tune the incoming energy to the actual edge that you're trying to absorb, you might get things that are similar to RICS, for instance. All sorts of extremely exciting things. Also, maybe a breakdown of various rules that we take for granted at high kV yields. What's certain is it certainly does work. And I'll show one last little thing, which I won't be able to show later in a week, because that was also something that dawned on us when we started doing this. And that's why Sean Collins, our colleague from the University of Leeds, came on board. He's a plasmonics expert. And he thought, well, we have an SEM, and plasmonics typically needs large-ish objects, typically metals, so silver, gold are your typical plasmonic metals, made of slightly weird shapes and sometimes 3-dimensional shapes. And you happen to put this into an SEM that gives you secondary, by definition, imaging capability. So if you have secondary, which is topographically sensitive and gives you some sort of 3-dimensional idea of what your sample looks like, and you combine this with your plasmonic maps, which would normally be in transmission and sort of flattening and projecting everything through the 3D structure, maybe you can get some really interesting information using plasmonics. So can we go towards plasmonic tomography in the SEM in EELS with this system? That's where we turn to our colleagues at the University of Cambridge, Emily Ringe, whose group makes all sorts of rather lovely samples, absolutely amazing things that we called tacos, chairs, and tents. The reason for this is the sort of triangular tent or triangular shape like this in French is called a Canadian tent, and Emily is from Canada, so when she came to visit us, I said, well, that's a Canadian tent, and so she kept it for the paper and then called it a Canadian structure. But the point of it is when we did all this EELS work, which is referenced here, we had no 3D information whatever. We had to go to the SEM to get the information or the shape of these things. What you can do now is actually do it directly in EELS, tilt your sample, so exact same type of sample. It's like a magnesium nanoparticle that is twinned, so it looks like a little bit of a taco or a chair like this. And you can tilt it like this. And if this will allow me to, so you can, hopefully it plays, yes, it does play. So this is a series of SE images at different tilts, showing you the structure of that particle sitting on a graphene grid. You see some sort of torn areas in a graphene. And at the same time, at each tilt, recording a full EELS map of the plasmonic response of this magnesium nanoparticle, putting it all into one big data set, and then using non-negative matrix factorization to pull out the various modes that you would normally see from these particles. This is what you see over here. And you'll notice in particular, there are modes that come out all the way down very, very low, so almost 1.6 or 0.6 eV in the tail of the zero loss. And the reason we can see those is not because we have super, super high energy resolution, it's just that the tail of the zero loss is so stable that you're able to see small changes repeatedly using statistical methods, so multivariate statistical analysis to pull out the small changes in the yields. And that allows you to essentially pull out all the face, age, and corner modes of that particle. If you're not convinced enough, you can even go one step further, look at a nice little nanocube. Hopefully this one will play also. So it goes a little bit faster. It's a cube. And you'll notice the facets are slightly eaten up, so it's slightly concave. And tilting from 25 to about 10 degrees, again on the support, you reveal all the factors in this plasmonic map. And if you look at the energy response, again, you get all the modes all the way down, 2 EV, 1.5 EV, and you can isolate the corner modes, the facet modes, even that sort of mode here in the middle that corresponds to the one that's sitting right in the middle where the concave facets sort of come together. Right. I think it's probably time I stopped. If you have any questions about the samples, the topics, how the instrument was set up, samples topic, ask me. How the instrument was set up, ask him. Although we also were there. Hashimoto-san, who's somewhere in the audience, also was there for some of the experiments over there. He was also part of the team turning the knobs. I'll just always make the joke that this was the photo at the end of the first visit. So Demi, Mike Dixon, and myself were all smiley. Sonoshi-san was sort of happy. Kaji-san still a little bit suspicious about what on earth we were asking them to do. Next visit along, everybody's smiling. We've got 10 samples, everything went perfect, and we can show atomic resolution in EELS. So just to say that this worked perfectly, and from where we stand, and again, not trying to sell it, but from a user facility where we have really high-end microscopes, but also a need for some sort of screening, but doing the same at low KV, this is really for us a unique tool. So again, if you have any questions, I'll be more than happy to give you all the dirt on why it doesn't work and how it doesn't work. And then you can go talk to the salespeople and they can tell you why it always works.